So in last class, we started discussing about optoelectronic transducers or optoelectronic detectors. Now, as part of that, in today's class, we would continue our discussions with photojunctions or photojunction devices, which are also used for optoelectronic detection. Now, uh, the most commonly used photojunction devices are the photodiodes and the phototransistors. So let us start with photodiode. So photodiode is basically the construction is similar to a PN junction diode. However, they are operated in the reverse bias mode. As you can see that a supply voltage is connected to ensure that the junction is reverse biased. So whenever the light or incident ray of light is imposed upon the depletion region. So suppose there is supposed to be a depletion region formed over here. So in the depletion region, when the light is entering, so the depletion region is normally considered to be a charge neutral region. So charge neutral atoms are present over here. However, the photon energy absorbed from the uh, light source will actually cause the neutral atoms to uh, uh, dislodge their electrons from the valence band. So if the electron is dislodged from the valence band, then you can say that a electron hole pair will be created, and in presence of the barrier potential, which is I mean uh, present due to the depletion region, the created electron and holes will be deflected on the opposite side, and this will eventually result in a flow of current. So normally, even when there is no biasing voltage applied, the depletion region will be still present. Suppose if this is the p-type material, this is the n-type material. So in the p-type material, you know that holes are the majority carriers, electrons are the minority carriers. In n-type material, you know electrons are the majority carrier and the holes are the minority carriers. So the depletion region is formed when some of the electrons jump from this n side to p side and some of the holes jump from p side to n side. So a charge neutral region is created at the junction, and if it is forward biased, the depletion region is supposed to shrink. If it is reverse biased, the depletion region is supposed to increase. So whenever light is entering this junction, so this charge neutral region, in this charge neutral region, some extra electrons will be created in the form of ionization of the atoms present over here. So the electrons will be actually attracted by the these positive charges over here, and the holes will be actually, so if we say the barrier potential over here is E. So in presence of the electric field in the depletion region, the electrons will be actually traveling through the depletion region towards the n side, and holes will be traveling from from the depletion region towards the p side, and later on when they are connected in reverse biasing voltage, so the electrons which have come, or free electrons which have come to this region, they will be attracted by this positive terminal of the battery, and the holes which have entered this region, free holes, they will be attracted by the negative terminal of the battery. So in this way, a flow of free charges will take place, and this will result in the increase in reverse bias current. So normally when uh, a device is reverse biased, some leakage current flows. Now that leakage current flows due to the presence of the minority carriers. So even without the incident light, if there is no incident radiation, due to the minority carriers, some current will flow in the absence of incident radiation. So that current is actually referred to the dark current over here. So without an incident ray, the amount of current which is flowing, that is called the dark current. Now, as the intensity of the incident radiation will increase, the amount of reverse leakage current will also increase, as more free electrons and holes will be generated in the depletion region. So as it is indicated in this characteristics graph, in the reverse bias region, with the increase in the intensity of the light, the amount of reverse leakage current is increasing. And for a specific voltage like shown over here for 5 volts, if for this constant voltage of -5 volts, if the different values of current at different values of intensity of light is plotted along the x-axis and the y-axis, so this sort of a graph is obtained, which is initially a bit non-linear due to the presence of the dark current, which is working as a sort of noise over here. Apart from that, the relationship is quite linear. So the illuminescence of the light can be directly related to in proportion to the change in current. Now, you know that in reverse bias case, the current is almost giving a saturated value. But in case of forward bias, you know that whenever the supply voltage is greater than the barrier potential, then the current will tend to increase significantly, as more voltage is applied, the more current will flow. So in the forward bias region, the graph is supposed to be ever increasing when it is entering the forward bias mode. So in the forward bias mode, beyond the barrier potential, the current will actually gradually increase almost indefinitely. So from there, it is difficult to realize a relationship between the intensity of light and the change in current, and it would be highly non-linear. So for this reason, this sort of photojunctions are normally operated in a reverse bias region, so that a linear relationship can be obtained between the intensity of light and the change in current. However, the current level is very low in microampere range, so the sensitivity of this sort of photodiodes will be low for lower intensity of lights. Now the symbol of photodiode is, there could be two possible symbols. So one is similar to the symbol of an LED, but the arrowheads are now in inverse direction, because it is not going to emit light, rather it is going to absorb light energy or photon energy. And another symbol could be by representing this symbol of a diode with this direction of flow of current I lambda. So lambda is actually going to indicate the wavelength of the light, because the wavelength of the light is actually going to be instrumental in generating the or increasing the amount of reverse flowing current. Now, as an example, this sort of photodiode can be used to, construct proximity sensors. So this could be one of the examples of how the photodiodes can be used. Now, if I discuss about the working of this particular type of sensor, so let me first discuss what are the elements present in this sensor. So first of all, in order to detect an object in close proximity, a transmitter should be there which will transmit energy, and a receiver should be there that will receive the reflected energy. So here, as the transmitter, an IR LED or infrared LED is used, and as the receiver, an IR photodiode is used. So the infrared LED is going to emit infrared rays which will be reflected back if there is any nearby object, and the reflected wave is going to be absorbed by the photodiode, the IR photodiode, and depending upon the intensity of the reflected wave, the photodiode will generate the reverse leakage current accordingly. So depending upon the amount of current received, it can be concluded whether there is a nearby object or not. And what are the other components present apart from the LED and the photodiode? There are a few resistors connected, a potentiometer, which will actually, by varying the potentiometer, it can be determined up to which distance a particular object can be detected. And there is an op-amp circuit over here. An op-amp IC is present over here. This red LED is actually an indicator LED. So when an object is detected, this LED is supposed to glow. And there are 3 power rails. 2 are for providing the DC supply, and 1 is for taking the output. So the output can be further used in some microcontroller in order to actuate some signal upon detection on a particular object. So how these elements are connected, that is shown with respect to this circuit diagram. So first of all, there is the op-amp. So the op-amp is actually working over here as a comparator circuit. So you know that in a comparator circuit, suppose if there are 2 voltages, one at the non-inverting terminal and another one at the inverting terminal. So if the voltage at the non-inverting terminal is higher, if V1 is greater than V2, then the comparator will send a high signal, and if V1 is less than V2, then the comparator will send a low signal. So this op-amp is going to work as a comparator over here, and now the 2 inputs at the non-inverting terminal and the inverting terminal, from where these 2 inputs are coming, let us have a look at those. So the inverting terminal, that input is coming actually from the potentiometer. So the 2 fixed terminals of the potentiometer are connected across the 5-volt supply and ground. So depending upon the position of the sliding contact, the sliding contact is actually connected with this negative terminal or non-inverting inverting terminal. So wherever the sliding contact is located, there will be a voltage division between the 2 components of the resistance in the potentiometer. So with respect to that, there will be a certain amount of voltage drop into this portion, which is actually fed to the inverting terminal. Suppose if the sliding contact is located right at the middle of this 10K resistor, so there will be 2 equal resistances. In the upper hand side, suppose there is 5 kilo ohms. In the lower side, from this fixed terminal up to the sliding contact, there is 5 kilo ohms. So if you can easily say that if the sliding contact is at the midpoint, and with respect to this sliding contact, the resistance of the 2 fixed terminals are equal, then the 5 volts will be divided equally among both the resistances. So it would give 2.5 volts. So that 2.5 volts is actually going to be inserted at the inverting terminal. Now if it is if the sliding contact is shifted downwards, then the voltage drop is supposed to decrease, and if it is shifted upwards, the voltage drop is supposed to be increasing. So depending upon that, where the sliding contact is located, a certain amount of voltage will be inserted at the inverting terminal. So that voltage is actually going to work as the reference voltage in this case. So with respect to this reference voltage, the voltage at the non-inverting term will be compared, and only when the voltage at the non-inverting terminal is higher compared to the reference voltage, then a high signal will be provided at the output of the op-amp, and when there is a high signal, a current is supposed to pass through the indicator LED, and the LED is supposed to glow, which would indicate that an object is being detected. And from this output terminal, the output can be also connected to the microcontroller or some other circuitry to actuate some process. Now, the input for the non-inverting terminal is actually coming from this branch. So in this branch is actually containing a photodiode and a resistor. And the input that is going to the terminal 3, the non-inverting terminal, is the voltage drop across this 10K resistor. Now, apart from that, there is another branch which is containing the IR LED and a series resistor. So as the IR LED is connected with the 5-volt supply, it will continuously radiate infrared rays. Now, if there is any nearby object, this infrared ray is going to reflect back to the photodiode. Now, upon receiving the infrared ray, reflected wave, the photodiode will the reverse leakage current flowing through the photodiode will increase. So as the current is going to increase, the voltage drop across this 10K resistor will also increase. And when this voltage drop across the 10K resistor is greater than the reference voltage, a high signal will be provided at the output side of the op-amp, indicating that an object is detected. And if there is no nearby object present in front of the IR LED, then no reflected wave will be received by the photodiode, and the current through the 10K resistor would be simply the dark current flowing through the photodiode, and that would not provide sufficient voltage drop, so that, and as a result, the voltage at the non-inverting terminal will be less than the reference voltage, and a low signal will be provided, which would mean that there is no nearby object. So this was one example how the photodiode and the LED can be incorporated together to form a proximity sensor. Now the working principle is briefly summarized over here as well, and now let us move on to the discussion on phototransistors. So phototransistors are also class of photojunctions. Now their working principle is similar to the working of bipolar junction transistors. However, where in case of bipolar junction transistor, you have a terminal from the base, so that is a 3-terminal device. However, in case of phototransistors, there are only 2 terminals for the collector and emitter, but the base is kept in such a way that there is no external terminals connected to it. Rather, there is an enclosure so that the light can enter towards the base. So in case of BJTs, where you have to provide external voltages between base to emitter and base to collector to provide proper biasing between the 2 junctions in order to operate in a particular mode of operation. So in this case, those external supplies are not connected. Rather, the incident ray is actually going to generate the current flowing through the base. So if there is a voltage source connected between the collector and emitter, so whenever there is light bombarding on the, towards the base, then due to the increase in the base current, the amount of current flowing through the collector is supposed to increase. So you know that the collector current can be related with the base current through this sort of an expression where beta is a constant, or it is an amplification factor, because depending upon this amplification factor, the collector current will actually be a multiple of the base current. So the more light which will enter towards the base, the more collector current will be. So in this way, if the voltage across the collector to emitter is plotted with respect to the current IC, collector current IC, for different intensity of light, we could have this sort of a characteristics curve. Similarly, for this case also, there will be a dark current, which is actually I mean a result of the minority carriers as well. So when there is no incident light, the current which will be flowing through the minority carriers, that is actually the dark current here as well. And for a higher intensity of incident rays, the amount of collector current is supposed to be increasing. Now here as well, for a fixed amount of voltage, if you plot the graph of suppose for a fixed voltage, if you plot the graph of the light intensity with respect to the collector current, you will have a similar wave shape that we obtain for photodiodes. However, one advantage of the phototransistor is that compared to photodiodes, the amount of current, the magnitude of current will be higher. So in case of photodiodes, where the current is in the range of microamperes, in case of phototransistor, the current will be in milliampere range, because this phototransistor is going to work as an amplifier, a kind of an amplifier. So the collector current is going to be amplified with respect to the base current, and due to this amplifying factor, the amount of current generated due to the same intensity of light will be more in phototransistor compared to photodiodes. So higher sensitivity can be obtained using phototransistor compared to photodiodes. Now, similarly, an example for phototransistors, how they can be incorporated to form a particular sensor. So here we are also considering a sensor which can be used to detect nearby objects, or calculate the distance of a nearby object. So this is the TCRT 5000 IR reflective sensors, and maybe many of you have used this for different projects, and if you have used the line, done the line follower project, then you might have used this sort of sensor to construct the sensor array for detecting the lines. Now here, this particular sensor contains actually two photo devices. One is the IR LED, and the other one is the phototransistor. So similarly, like the previous sensor which was discussed, infrared ray will be emitted from the IR LED, which will be reflected back if any nearby object is there, and that reflected wave will be received by the phototransistor, which will result in a current flow through the collector to emitter of the transistor. So the connections between these photodiodes and the LED and the phototransistor is shown over here. So the LED is connected in series with the resistance, and that is connected with the supply. So the LED is going to continuously emit infrared rays, and if that ray is reflected back towards the transistor, then the transistor will receive the reflected radiation, and that will actually cause a current flow through the increase in current flow through the collector to emitter. So that same current will actually flow through this 10K resistor, and from this 10K resistor a output can be taken, which can be connected to the microcontroller as well in order to further process the data. And in parallel with this 10K resistor, a separate branch could be there where an indicator LED will be present. So a portion of the current will flow through this indicator LED, which will indicate that a nearby object is detected. So these are two examples of one with photodiode and one with phototransistor, how a particular sensor can be designed using these devices. Now a few more examples, but regarding the other type of transducers that we discussed in the previous lectures. And for example, we would take the pressure measurement by construction of pressure measurement sensors using the different transducers which have been discussed so far. So the pressure measurement sensors that I'm going to discuss, they are going to be of electromechanical type. So in this electromechanical pressure measurement sensors, so there will be two stages of mainly two stages of energy conversion. One is actually detecting the physical change by some mechanical means to sense the pressure actually, and then converting the converting that signal by electrical means to further convert it into some analogous electrical quantity. Now, so this means that there needs to be two elements for this sort of sensors. That the first one is a primary sensing element, which would convert the pressure into displacement by some mechanical methods or mechanical transducer. And the second one is actually an electrical transducer, which is actually going to convert the displacement into the analogous electrical signal. And this type of electrical transducers, as they are employed in the secondary stage of detection, so they are actually called the secondary transducer. So I should not say in the first case I said that mechanical transducer, but actually the energy is not getting converted from one form to another, because pressure is getting converted into motion. So actually I cannot say that that is a mechanical transducer, but that is a sensing element that is sensing the signal, and it is converting the variable into another type. So some commonly used mechanical sensing elements are shown over here. So the first one which is shown in here is called the bellows. The second one is called the diaphragm, and the third one is called a Burden tube. So all this type of mechanical sensing elements must be made of elastic material, and they must operate within their elastic limit, because like any electrical device, you have to operate it within its rated voltage or current. Similarly, for the mechanical devices, they also, if they are made of elastic material, they have to be operated within their elastic limits so that they don't get damaged. And to discuss the second point, the stresses produced in the sensing element establishes an equilibrium with the pressure to be measured, and eventually that converts that pressure into an analogous displacement of the particular sensing element. Now the choice and design of the sensing element can vary depending upon the magnitude of the pressure to be measured. Now if I talk about the bellows, so it is actually going to have inlet from where suppose some gas or liquid can enter into its chamber. So when it is experiencing some force in its inner chamber, so it is supposed to experience it is supposed to expand due to the experience of the pressure. So when it is expanding, it will have a motion in this direction or displacement in this direction, and when it is releasing the pressure, it will compress and it will have a motion or displacement in the opposite direction. Similarly for diaphragm as well, suppose in one side of an enclosed chamber the diaphragm is connected. So if there is some applied pressure into this chamber and that pressure is greater than the atmospheric pressure, then the diaphragm is supposed to be shifting upwards, or there will be motion in the upwards direction. And if suppose the outside pressure is greater than the pressure inside this chamber, the diaphragm may shift inwards or in downwards direction. So in this way, the pressure can be actually converted into linear motion or displacement. And the third type of mechanical sensing element, which is shown over here, that is a C-shaped burden tube. So you can see that there is a curved elastic tube, and when some pressure is experienced by this tube, suppose some gas or liquid is entering into this tube, so that gas or liquid or fluid will actually cause some force in per unit area of the inner surface of this particular tube. So that will actually cause the curved shape to deform or straighten a little bit from its initial position. Suppose the more the pressure, it will try to get straightened from its initial position. In this way, a motion can be there in this direction as indicated over here. So the more pressure will be there, the shape of the burden tube will try to deform more. So using these mechanical sensing elements, the pressure can be first of all sensed and converted into equivalent displacement. That displacement can be coupled with an electrical transducer, which will convert the displacement into analogous electrical quantity. Now, the electrical transducers could be resistive, inductive, capacitive, or piezoelectric types. So if we first discuss about resistive pressure transducer, so one arrangement can be obtained such that the primary sensing element is a diaphragm, and the secondary transducer or electrical transducer is a strain gauge which is attached to the diaphragm. So as you can see in this figure, on both sides of the diaphragm, two strain gauges are attached. So depending upon the pressure on the upper side of the diaphragm and the lower side of the diaphragm is supposed to be shifted upwards or downwards. And with respect to that, one strain gauge might get expanded and the other one might get compressed, and that will actually that stress is going to cause the change in resistance in the two strain gauges. And if the two strain gauges are connected in a bridge circuit, then from the bridge circuit the corresponding change in voltage can be observed. So the stages of or flow of operation will take place in this in this chronology. So first of all, the differential pressure is going to be experienced by or sensed by the diaphragm as deflection of the diaphragm or displacement of the diaphragm. Then difference in the two, that displacement is actually going to cause the change in resistance, or there will be a difference in the resistance of the two strain gauges. And furthermore, these two strain gauges can be connected with an output circuit, which could be a bridge circuit, from where finally the output can be further processed. Now, in most of the cases, silicon is used to construct the strain gauge because they have high piezoresistivity. And if some material is having high piezoresistivity, then the gauge factor is supposed to be increasing, and if the gauge factor is increasing, the sensitivity of that particular strain gauge is supposed to increase as well. So if you remember from the discussion of strain gauge, the gauge factor was represented by 1 plus twice mu plus delta rho by rho divided by delta L by L. So this term was referred to as piezoresistivity. So if some material is providing higher piezoresistivity, which means that the gauge factor is going to increase and the sensitivity will also increase. Now, the majority of the resistive pressure sensors are actually formed by strain gauges, which are made of silicon, into a diaphragm which is also made of silicon. So this allows the same fabrication technology to be used to form the sensors, both by forming the diaphragm and the strain gauges using the same technology. So it helps to ease the fabrication process. And in most cases, 80% of the pressure sensors are resistive pressure sensors are of this type. And as semiconductor materials are used, the size of the sensors can be miniaturized. So in that sense, these sensors can be called silicon micro-machined pressure sensor. Now, the disadvantage of the resistive pressure sensors is two disadvantages are three are highlighted over here. The first one is that they are low sensitivity. So the signal amplitude will be very low. So, or the change in signal will be very low. So the output signal has to be amplified further to detect the significant changes. And as resistive elements are used, they are dependent on temperature. So some sort of temperature compensation is necessary, and they also possess a non-linear characteristics. So these are some disadvantages of this sort of pressure sensor. Now, about temperature compensation. Now, this sort of arrangement is itself useful to compensate the pressure to some extent, compensate the temperature variation to some extent. If two strain gauges with identical design and materials are used, then instead of one strain gauge, if two are used, they are sometimes useful to eliminate the effect of minimize the effect of temperature variation. So suppose one strain gauge, if it is R1, the other one is R2, then if we say that we have a bridge circuit where these two strain gauges are going to be connected, suppose R1, R2, and two other resistances are there, those are R3 and R4, and there is a supply voltage, and we have the galvanometer. Now suppose if there is no temperature variation, suppose both this and there is no strain as well, and we can consider as identical materials are used and identical dimensions are used. Both the strain gauges are having a equal resistance of R as their unstrained resistance, and also without any temperature variation. So in that case, in the balance condition, you can say that R1 by R2 should be equal to R3 by R4. Now, if there is some temperature variation in both R1 and R2, so what will happen? Suppose R1 will get increased from its initial value of R by delta R, and as R2 is also having the same initial value and the same type of material, so the change in resistance should be identical for R2 as well. So this actually keeps the ratio to be equal as before, because the change in the resistance due to change in temperature is equal for both the cases. Now, if suppose now some strain is also applied, so suppose due to applied stress or strain, now there would be further variation in the value of the resistance of R1 and R2. Suppose Rs represents the change due to strain, and suppose one of the strain gauges, its value is going to be slightly increased. Suppose that for the other one, its value is going to be slightly decreased. However, the change in this is the original resistance. This is due to applied stress or strain. One is having a positive component of resistance due to the applied stress, and another one is having a negative component due to the applied stress, and the other component which is due to the temperature variation. So still these two components are going to be equal because the similar type of material is used. So in this way, if in two of the arms, two identical strain gauges are used, to some extent the temperature compensation can be achieved. Now here it has to be considered as well that for the other two arms, those two resistances are also have to be made of similar material, so that the uh, change in temperature is identical for those two as well. So to have achieve further accuracy by compensating the temperature, even for some cases, in all the four arms, identical strain gauges are used so that the temperature compensation can be done. Now, another type of resistive pressure sensor would be formed by using the bellow as the primary sensing element and a variable resistor as the secondary transducer or electrical transducer. In this case, you can see that we have a variable resistance over here, and its sliding contact is connected with the bellow through a shaft. So whenever there is in presence of applied pressure, there is some expansion or compression of the bellows, the position of the sliding contact will change, and according to the position of the sliding contact from these two terminals, the resultant resistance will also change, and with respect to the change in resistance, the further output can be processed. Now, in the in this path of the movement of the bellows, a spring is also attached. So the purpose of the spring is to allow some amount of damping, so that the presence of overshoot can be eliminated, so that there is no sudden change in resistance that is going to be creating some overshoot in the amount of current or the amount of voltage, rather so that due to the presence of the spring, the change can be gradually transferred towards the change in resistance, so that there is no sudden rise in voltage or current which will result in an overshoot. So these were two resistive type of pressure sensors. Now if we talk about inductive pressure sensor, similar arrangement can be used by replacing the potentiometer with an LVDT. So here for the primary sensing element, bellow can be used, and for the secondary transducer, as the secondary transducer, an LVDT can be used in case of uh, the variable resistor. So in this case, the bellow will be coupled with the uh, ferromagnetic core of the LVDT. So if you remember the construction of LVDT, it contains one primary coil and two secondary coils, and depending upon the position of the iron core, the induced voltages at the two secondary sides will differ from one another, and the final output from the LVDT can be taken as a differential voltage difference between the voltages induced in the two secondary coils. So here the pressure is first of all converted into displacement or linear motion or movement using the bellows, which is further transferred to the LVDT, and LVDT detects the change in displacement in terms of change in mutual inductance, which further is converted into change in voltage. So in this way, using LVDT, inductive pressure transducers can be formed. And another example could be by using the C-shaped Bardon tube as the primary sensing element and LVDT as the uh, electrical transducer. So here, instead of the bellows, the Bardon tube is actually coupled with the iron core of the LVDT. So when there is some fluid passing through the Bardon tube, its shape will shape is supposed to change, and suppose if it is experiencing force in the upwards direction, the position of the core will actually deviate from its null position, and when it is deviating from the null position, the voltages induced at the secondary sides will differ from each other, resulting in a differential voltage as the output of the LVDT. So in this way, the output of the LVDT could, or the change in voltage provided by the LVDT could be proportional to the change in pressure. So lastly, in today's lecture, I will conclude with two more examples of a capacitive pressure transducer. So for capacitive pressure transducer, suppose one example could be like using the diaphragm as the primary sensing element, and the capacitive transducer can be formed to convert the displacement into electrical quantity or change in capacitance. So here in this structure shown over here, there is a diaphragm as indicated over here. So that the diaphragm is actually made of conducting material, so that itself the diaphragm itself can be working as one of the plates of a parallel plate capacitor. And as the other plate of the parallel plate capacitor, a metallization layer is used, indicated by this black surface over here, which is placed on top of a ceramic or glass substrate, which is a non-conductive substrate. So these two are going to work as the two parallel plates of parallel plate capacitor. And depending upon the pressure difference on two sides of the diaphragm, so there will be a through hole through the metallization layer, so that some fluid can pass in this enclosure between the diaphragm and the metallization layer. And depending upon the pressure difference on both sides of the diaphragm, the diaphragm may move in the upwards direction or the downwards direction, changing the distance between the two plates. So this type of formation of a capacitive pressure transducer is based on the principle of variable displacement type capacitive transducer, as the capacitor is going to vary with respect to the change in distance of the two plates. So the variable capacitor can be represented by this equivalent circuit symbol. And another option of forming a capacitive transducer could be the formation of a differential capacitor design. So in one of the previous lectures, you have seen that a differential arrangement of capacitive transducer was discussed, where there were three capacitive plates. Two of them were considered to be fixed plates, and one of them was considered to be the movable plate, which could move on along the vertical line, varying the distance between the movable plates and the two fixed plates. So this sort of an arrangement can be also done by placing a metallization on the upper side of the diaphragm as well. So similarly, on top of a ceramic substrate, another metallization layer is used. So in this case, this is supposed P1, this is supposed P2, the two fixed layers, and the diaphragm is actually going to work as the movable plate. So with respect to the pressure difference, the diaphragm will either shift towards the upper plate, reducing the distance between the upper plate and the diaphragm, and increasing the distance between the lower plate and the diaphragm. And if it is shifted downwards, then just the opposite will happen. And in that sense, actually, a differential capacitive design can be obtained. And if the differential capacitive design is obtained, then from a bridge circuit, it can be further processed to detect the change in pressure with respect to the change in voltage, as discussed in one of the previous lectures while discussing the differential capacitor design. Now my internet connection is showing to be a bit unstable. Can you hear me?
Yes, sir.
Okay, so this actually concludes the discussion that I wanted to conduct regarding the different types of transducers. Now, for your further reference or better understanding, you can refer to these articles from the book of Shawnee. So in those articles, all the topics are discussed in more details. So I hope that you will have a better idea if you go through those articles. Now, if you have any question regarding to this lecture, you can ask the question now. After the questions, we can move on to the discussion of where I will discuss about the answers of the quiz 1, so that you can identify that where you have made the mistakes. So if there is any question, you can ask.
No questions, sir. Sir, is there a way to see our submissions after Google Classroom quiz?
Now I'm not releasing those submissions.
Sir, could you?
Yes.
We can see the question.
Okay, so let me start. So first of all, in this question, a mathematical problem was there So here you are given values of the P, Q, and S. So S would be actually you have to, it will be different for the different students depending on their student IDs. Now, when you have these three values known to you, you can easily calculate R. So when you know R, the value of this resistance, you can also calculate the R Thevenin quite easily. So I hope that you know that formula, which is RS. So apart from that, you the other quantities which is given to you is the sensitivity of the galvanometer, or it is the current sensitivity actually, the 200 millimeter per microampere, then the resistance of the galvanometer Rg. So with respect to that, you can, and one more thing, that is the uh, deflection, the required deflection, that is also given. So theta is also given. So from here you are calculating R Thevenin, you know the current sensitivity, you know the galvanometer resistance, you also know the required theta. So from the expression of theta, you can use the expression of theta uh, to determine the change in resistance. So for this part, this math, the students who could have uh, uh, done up to the R Thevenin, or even for the value of R, depending upon that, I have given some partial marks. Now those who have done up to this portion as well, which is calculation of the delta R, they got the full marks. Other than that, those who have tried to obtain up to RTH, I have also given some partial marks to them. And I think this one is actually from similar to a problem of your example, which is 14.10. So you can further refer to that particular example to uh, have an even better idea. Now, in the beginning of the class, one of the students was saying that while solving the math problems, he saw that there are some minor mistakes in the calculations. So that is actually true. So in that book, there are some minor mistakes while doing the calculations. Maybe the formulas are written properly, but while putting the different values or doing the calculations, there are some uh, uh, mistakes. So you should, while you are practicing those examples for your midterm, you should try to keep those things in mind. Those are uh, uh, actually easily identifiable mistakes. If you go step by step, you will easily identify what are the mistakes. So keep that thing in mind. So this answer will be actually different for different students. So I'm not doing the entire calculation. Now moving on to the next question, as shown over here. So an initial resistance of 10 mega ohm was specified, and it was specified that it has a temperature coefficient of 50 parts per million per degree Celsius change. So what is the possible change in resistance for 2 degrees Celsius rise in temperature? So first of all, 50 parts per million, you can represent it by 50 divided by 10 into 10 to the power 6. And what fraction of the 50 parts per million of 10 mega ohm is? You can multiply this with 10 mega ohms. So this will easily cancel out. So you'll have 500. And if you multiply, this is for 1 degree Celsius change, and for 2 degree Celsius change, obviously it would be 1000 ohms. So the answer for this one is 1000. Now these particular problems, relates W with respect to X, Y, and Z. And if you remember the lecture where the different combination of errors were discussed, so you can see that the variables X, Y, and Z are related through multiplication and division, and X is also having a power of an exponent. So first of all, just let us consider the multiplication and division. And for that, you know that the relative error in W should be the summation of the relative error in X, Y, and Z. And as X is raised to the power of 2, considering the power of an exponent, the 2 will be multiplied with the relative error of X. However, for this particular problem, the errors are given in terms of absolute values. So the first thing would be to convert these into equivalent relative errors. So for the first case, the relative error will be 2%. For the second case, it is also 2%. For the third case, it is also 2%. So according to this formula, it will be 2 into 2 plus 2 plus 2, which is 8%. So you can easily say that this is one of the answers. And if you take 8% of 50, so the absolute error in 50 would be plus minus 4. So this is another answer. So there are two correct answers in this particular question. So what I did for this sort of questions which are having multiple correct answers, I also try to give some partial marking. So if a student could mark or choose one of the correct options without marking any other wrong answers, then I have given some partial mark. But if the student is selecting one correct answer and one wrong answer, in that case I haven't given any partial mark, because one correct answer and one wrong answer is actually nullifying each other. But if one answer was chosen correctly, then some partial marks was given for all the multiple choice questions actually. Now, which of the following statements are true for Carey-Foster-Slideware bridge? So can be used for comparing two nearly equal resistances. It is okay, it is true. Now, typically suitable for measurement of resistances less than 1 ohm. So this is actually wrong, because resistances less than 1 ohm correspond to low resistances, but Carey-Foster bridge is normally used for medium range resistance measurement, and the Kelvin bridge is used or more suitable for measuring low resistances. The last one, which is saying that it is not possible to determine the value of an unknown resistance if the resistance per unit length of the slide wire is unknown. So it is actually wrong, because it is possible to determine the value of unknown resistance if the resistance of the slide wire is not known. So in that case, you have to use two known standard resistances. You can refer to the lecture or refer to the book if you have any confusion regarding this. Now this question is quite straightforward. Now what condition has to be satisfied in order to get maximum bridge sensitivity from Wheatstone bridge? So it is P by Q or R by S equals 1, or you can write P equals Q equals R equals S. So any of these two were considered to be correct. Even some students just wrote P by Q equals 1 or R by S equals 1. So for this quiz, I have also considered those as correct answers, because your marks were not that good. So for this quiz, I have even considered this sort of answers. What is the purpose of using guard ring? For this question also, different types of answers were there. But in general, you can say that to bypass the leakage current. or some of the students have written to separate the surface resistance from the volume resistance. So different types of answers were there, but if the answers were logical, then I have given the marks. For this question, normally it could be answered from without doing any calculation. So first of all, let us see what is given in the question. So there were 20 readings which had an average of 30 volts. Now if two more readings are taken and the two new values are 26 and 34, what would be the change in the mean, or it will remain unchanged? So for this case, it will remain unchanged because the two new values are symmetric around the mean. So the mean is 30. So one is 4 greater than the mean, one is 4 less than the mean. So they are actually symmetric with respect to the mean. So in that sense, you can say that the mean will remain unchanged. But if the two new, because one is suppose -4, I mean 4 less than the mean, another one is 4 greater than the mean. So the decrease in one value is getting compensated by the increase in another value. So in that sense, you can say that the mean will remain unchanged. But if the increase or decrease was not symmetrical, then the mean would definitely change. So if you want to do calculation, then you can do it like this: 20 into 30 plus 26 plus 34 divided by 22. So you can also do the calculation if you want. So you would see that it is actually supposed to give you 30. And for the standard deviation is given as 4. And when the new readings are added, each of the readings, if you consider the magnitudes of the deviation from the mean, you'll see that both of the new values are actually 4 volts away from the mean, if you consider the magnitudes only. So as the deviation from the mean is equal, and that is equal to the standard deviation, so in that sense, you can also say that the standard deviation will remain unchanged in this case. And this last question shown over here. So which of the following is true for a figure? So the first one, quite obvious that it is used for high resistance measurement. Then the second option, in case of open circuit, the entire current flows through the deflecting coil. This is wrong, because if you go back to the lecture or the article from the book, you will see that according to the construction of the discussion done, in case of open circuit, most of the current will actually flow through the control coil. Now, separate magnetic fields causes opposing torques in the deflecting coil and the control coil. Now, the torques produced by the deflecting coil and the control coil are opposing in nature. However, both the coils are placed in a common magnetic field, not in separate magnetic fields. So in that sense, this option is also incorrect. And in case of short circuit, deflecting coil force is greater than the control coil. This is actually correct, because in case of short circuit, most of the current flows through the deflecting coil. So the deflecting coil force is supposed to be greater than the control coil. So these were the correct answers. Now I will upload the recorded video if you need. If you can go through the answers again and try to identify where you have made the mistakes. Now regarding the time limit, so the time limit had to be restricted in order to make sure that there is less chances of plagiarism. Maybe I have given you 12 minutes, but maybe 15 minutes would have been ideal, but some restriction had to be there. Now if you are trying to collect answers from here and there, or looking for answers in your from your lecture materials or from your books, or consulting with your friends, then you are certainly going to lose some time. Okay, so uh, from the next quizzes, I would expect that you would prepare well, and instead of looking for answers during the exam, you or browsing in the internet, because some of the students have also browsed the answers, some uh, 2 or 3 answers directly from the internet. It is quite obvious to uh, uh, see by the nature of the answer, because a lot of students were there whose answers were directly from just copy and paste from the internet. So if you're doing that, browsing from the internet and giving the answers, or looking for from your course materials to find the answers, or consulting with your friends, then you're definitely supposed to not have enough time to answer all the questions. So keep this thing in mind from your next quiz.
Sir, about the midterm exams, our mathematical questions will be from the same type of the examples.
Yeah, similar type from the examples, but not directly. Uh, exactly, the example problems will not be put into the question. Okay, there could be slight changes either in the form of values, or uh, uh, I mean, the concepts of multiple example problems can be merged together. So you have to be prepared for that. Don't expect that exactly the same question from the example is going to be coming in the exam. Okay.
আর স্যার এক্সাম্পলের বাইরে কি আমাদের কোনো কিছু প্র্যাকটিস করতে হবে, মানে আপনি যেগুলো দিয়ে দিয়েছেন তার বাইরে?
এক্সাম্পলের বাইরে করতে হবে না, কিন্তু এক্সাম্পলের প্রবলেমগুলা বুঝে করার চেষ্টা করবা, যাতে ধরো একাধিক প্রবলেমের কনসেপ্ট মিক্স করে যদি তোমাদেরকে কোনো প্রবলেম দেওয়া হয়, সেটা যাতে করতে পারো। ধরো শুধু একটা এক্সাম্পল করে আসছো, এখন ওই এক্সাম্পলের সাথে আরেকটা এক্সাম্পলের কিছু পোর্শন মিলাই দেওয়া হবে। তো সেই ক্ষেত্রে তোমার যদি দুইটা সম্পর্কে ক্লিয়ার আইডিয়া না থাকে, তুমি হয়তো ম্যাথটা ওই সময় বুঝে করতে পারবা না। এই জন্য চেষ্টা করবো যে প্রতিটা এক্সাম্পল বুঝে বা স্টেপ বাই স্টেপ বুঝে করার জন্য। আর যেটা বললাম, ওখানে এক্সাম্পল গুলো যখন করবা, হয়তো প্রসেস পুরাটাই ঠিক আছে, কিন্তু ক্যালকুলেশনে কিছু ভুল হয়তো পাবা। তো ওগুলা কিছু কনফিউশন রেজ করতে পারে, এই জন্য ওটা মেনশন করে দিলাম এখানে, যাতে করে প্র্যাকটিস করার সময় ওই কনফিউশন গুলা না হয়।
স্যার আপনি যে বললেন স্যার, মানে কয়েকটা কোশ্চেন মিলিয়ে হয়তো একটা কোশ্চেন দিতে পারি স্যার, ইন কেস আমি কোনো পার্ট কমপ্লিট করতে পারলাম না, তাহলে কি আমি স্যার পার্শিয়াল মার্ক কি পাবো?
For a math problem, as much as you make progress, depending upon that, you are definitely going to get partial mark. Suppose there are 2 or 3 uh, I mean answers that you have to determine, as much as you can complete with respect to that, you will get partial marking.
Yes.
Because even if the answer is incorrect, as it is going to be a written exam, if you can write the formulas properly, and if your process is correct, even if the final answer is wrong, for your process you will also get partial marking, because it's a written exam.
Sir,
Yes.
sir, what about our mid syllabus? Will it be up to what you will discuss in the class of Thursday, or you will set some other syllabus?
Well, for now, it would be up to what I discussed on Thursday. Now, regarding the I mean exam duration, as you are discussing about the midterm, so let me discuss a bit more. So the syllabus would be up to what I discussed on Thursday, and the duration of the exam will be of 1 hour. That's what I have thought up to now, and maybe I'll have a exam of 60 marks, where you have to answer 3 questions. Each of the questions will be having 20 marks each, so making a total of 60 marks. And maybe you have seen a guideline which is circulated by the department. So I think the department is going to assign all the teachers to give virtual invigilation. So before the exam, you will be divided into several groups. So each of the students will be under a particular invigilator. So go through that guideline. And regarding the question pattern, as it is going to be a written exam, so you might have to do some derivations or write some theoretical discussions, or you have to do some maths like a regular exam, a written exam that you give in case of physical examination. So that's it up to now regarding the midterm exam. If there is further guidelines, I'll contact the CR or inform you in Google Classroom. And one more thing I had, is the CR over here? Is Abid over here now? Okay, has the CR informed?
Sir, we are having another class. Nice.
Okay, so just one more thing. Did the CR inform you anything about the second quiz?
Sir, I think it is our mid-year din hobe, maybe midterm exam pore.
Yeah, so I had a discussion with the CR. So mid is supposed to be on 21st of November, right?
Yes, sir.
So mid exam would be from 10:30 to 12, and your quiz will be starting from 2:30. Okay. So the mid will be a written exam. However, the quiz 2, it would be again a MCQ and short question based exam. And for quiz 2, your syllabus would be the AC bridge circuits plus from the transducers, I mean what was discussed before, optoelectronic detectors. Okay, so that would be your syllabus for quiz 2, and it will be taking place on the same day of the midterm exam from 2:30. So you can keep that in mind. Okay, so as you have another class, I am concluding today's session. And
So,
yes.
Regarding the last quiz, I don't know what exactly happened because I submitted my quiz within the time duration. So I'm only